Okay, in this mini lecture, we're going to do forces on submerged surfaces, but there's a difference. These surfaces are no longer planar, and so this is forces on non-planar curved, non-planar submerged surfaces. And so this is hydrostatic forces. These are pressure forces, just as we've been doing. And our approach to them isn't. It's more of a trick. It's more of a dodge. And so in this case, I'm going to teach it via an example rather than doing it with just the theory. And so we're going to consider something we are more familiar with, which is a tank with a flat side. We're going to consider a curved section of it. It goes something like this. So there's nothing different here except this part bends. It's not a planar surface, so it's outside the auspices of those formulas we derived in say the last lecture. And just say there's a free surface up all the way up at the top. And I said I was going to do this by example. Let's say that this distance here is h1, and all the way down is h2, just to give us a sense of a couple dimensions. Let's say that across to here is D, and let's say it's B into the page. Just like that. So that's our picture here, and the question, and it's this sort of question is where we can use this dodge in so many cases. What's the net force on the curved section? And so, in reality, what would the actual forces acting on this curved section? They look like this. We have our curved section, and it's similar to what we had for a plane wall. On the plane wall, we went in and we said, well, there's this force acting here, this force acting here, this force acting here, this force acting here, and so on. And they got smaller as you get towards the surface because the pressure is lower and the forces are less. And we could do those integrals. We could get those integrals in terms of the moment of inertia formulas, these geometric properties of whatever piece of this surface we were considering. Same thing in reality happens here. And so at the bottom you have a force acting here. But not only do the lengths of the arrows change according to how deep you are within the fluid. I'm trying to draw them shorter. I'm shading this badly. Shorter at less depth and longer. But the direction also changes. And so you could take the same approach. But in general, that's going to lead to intractable integrals. So you can write down an integral expression for what these are, given the shape here, so they're usually done numerically. You can approximate analytical integrals with a sum, and so that's what's done on a computer usually, and that might be how this would be done here. But for this type of question we're asking here, what's the net force on that curved section? We don't actually need to parse it down to this level. And so what we do is almost like cheating. If you recall when I talked about pressure acting on surfaces, I made this emphasis that they're kind of real or fictitious, just made up surfaces. And so let's pretend those two surfaces exist. And so we just kind of imagine them being there. And let's take out this piece of fluid and do a force balance on that. And so these are our shapes of that piece of fluid, and we have a force on the top, and it's a distributed force here, and it's equivalent, let's call it F1. And there's no secret what its formula is. It's gamma. It's a plane surface, HCA. And we know what all these things are. Gamma is probably given in the problem. We'll say it is. HC is the depth of the centroid. And so from the surface, the centroid of this plane is at H1. And the area of this is D times B. Okay, that's the force down there. And there's a distributed force on this side, and we have formulas for that too, because it's a planar surface, and so we can draw a big F2. And using those formulas, well, we know what F2 is. It is gamma HCA, which in this case is gamma. And the depth of the centroid, it's a rectangular face, so the centroid's halfway down. So it is 1/2 H1 plus H2. It's the average of H1 and H2 is the depth of the centroid. That's where this formula comes from. And the area is B times H2 minus H1. So this height here is H2 minus H1, and then the depth of that into the page, making up the area, is then B times H2 minus H1. And you can write this a little bit more compactly, 1/2, and it's H2 squared minus H1 squared B. It's not clear, that needs to be done. The main thing I want to get across is that we know this force and we know this force. And then, if you recall, in our first example with hydrostatics, we did the pressure on the bottom of this flat-bottomed tub, and we found there that the net hydrostatic force on the bottom was, if we considered it from a pressure perspective, was just equal to the weight of the fluid above. And we can say that right here. And that weight would just be equal to the gamma volume. Now, let me just draw that again and summarize what we know. And so there's our free body diagram, our body being that chunk of fluid. W is equal to gamma V. And we had F1 on the top, F2 on that side. And those have to be balanced by what we wanted as our answer, and so that we could resolve it into a vertical, horizontal, that's F sub H, components. And so FH, the net horizontal force on the curved part, is equal to F2. And FV, the net vertical force, is equal to F1 plus W. And in some sense, that's the answer. You might want to know more about these forces, where they effectively act. get them into a single vector with an angle and an effective location, in which case you would take moments about some point, like we took moments for those other formulas for the planar surface. But lots of problems don't require that even. And so you're probably good from statics of figuring out net moments and so on, and figuring out where these forces would have to act. We're not going to consider that here. The neat trick is to put in these flat surfaces to avoid having to actually deal with this curved surface. We would have to be given the geometry sufficiently enough to describe what this V is. And I guess one last thing I want to note here is that the weight acts effectively at the centroid of the volume. And so there's some center of mass, and that's where the mass effectively acts if you resolve it into a single vector.